Hello, Math 109 students. We're moving on to Chapter 3. So Chapter 3 is focused on the concept of functions. What are functions? What can we do with functions? Functions is a humongous topic in mathematics. We're going to get into just some, part way into the topic of functions in Chapter 3. In general, the way that I like to think of functions is as a machine. So here's this machine. All right, it takes something into it and it spits something out of it. Let's say that this machine is called F. And this machine takes something into it and it does something to it. It takes something in that we're going to call X. All right, hold on. We're going to call it X. And it's going to multiply that thing that comes into it, which we're going to call X. It's going to multiply it by 2. And it's going to subtract 1. So whatever comes in that machine gets multiplied by 2, and then that result gets subtracted by 1. So let's say 0 goes into the machine. Then what comes out of the machine? Well, it gets multiplied by 2, that's still 0. It gets subtracted by 1, that's negative 1. So 0 goes in, the machine shakes around a little bit, and then it spits out negative 1. So then you have this ordered pair. The input comes first, that's 0. The output, negative 1, comes second. And there's an ordered pair. The input and the output, the x and the y. The x and the f of x. F of x being what the function spit out. All right, let's say you put 5 in there. What got spit out when you put 5 in there? 10 minus 1 is 9. So we have another ordered pair, 5, 9. And so on and so forth. That's kind of what a function does. All right. Let's look at some things that the book says about this. So we first talk about, in the book, we talk about what's called a relation. A relation is something way more general than a function. A relation is kind of what it is, what it sounds like. It's a relationship. It's a relationship between two sets of numbers. This set of, or maybe not even numbers, this set of things is related to this other set of things in some way. That's a relation. All right. If x and y are two elements in these sets, and if a relationship exists between x and y, then we say that x corresponds to y, or that y depends on x, and you can write it like this: x corresponds to y. There are a number of ways to express relations between two sets. For example, y equals 3x minus 1. That's a relationship. Y depends on x. X and y correspond to each other in some mathematical way. All right. So for that particular case, kind of like what we just saw, x serves as the input to the relation and y is the output of the relation. You can express a relation as an equation like that. You can express a relation as a graph. You can express a relation as a mapping, which is like in example 1. You can express a relation as a table. You can express a relation as ordered pairs. There are lots of different ways to express kind of the same thing. All right. A mapping, a technique called mapping. A map illustrates a relation by using a set of inputs and drawing arrows to the corresponding element in the set of ordered pairs, instead of outputs. Ordered pairs can be used to represent this, which is kind of what we just saw. Look at this. Relation here. It's a mapping. It maps the state name with the number of representatives for that state. So your first order pair might be Alaska, 1. Your second order pair might be Arizona, 9. All right, and so on and so forth. All right, and that would be a relation. Okay, now what about a function? A function is a special kind of relation. Let's read what the book gives as the definition. It says, let big X and big Y be two non-empty sets. All right, so big X is a set of inputs. It's not just one input, it's a whole set. That's why it's a capital X. And big Y is a whole set of outputs. A function from X into Y means something where X is an input and it leads to Y being an output, is a relation that associates each element of big X, meaning each of the inputs, with exactly one element of big Y. It means exactly one output. So each input can be associated with only one output. Notice it didn't say each output can only be associated with one input. That's important to distinguish the difference there. Let me give you another way to think about it. What makes functions kind of set apart is that they are predictable. They have predictive power. If you know the input, there is no question about what the output will be because it's only one possibility. So it's perfectly predictable according to the input. It's perfectly predictable according to the input. So if everybody's looking at, let's say this right here. If everybody's looking at figure 4 with the dog, the duck, and the rabbit. Here's the animal. Here's the life expectancy. Everybody can see this information, and I say, Susie, predict the life expectancy of a duck. Susie would be able to easily say 10 years. And if I said, okay, Bob, you give me the life expectancy of a duck, he would also say 10. Everybody looking at this would say 10, unless they were just being obstinate. But it's perfectly predictable according to the input. If you see the input, there's no question about what the output would be. That's what makes a function, not just a relation. However, look at figure 3. Let's think about the difference here. If I said, hey, everybody, what's Dan's phone number? Everybody would say the same thing. Everybody would say 5552345. But if I said, hey, everybody, what's Colleen's phone number? Then there would be a question mark. Wait a minute. There's 2 of them. I don't know which one to give. It's not perfectly predictable according to input. Because there's more than one possibility. There's at least 2 here. So this is not a function because this input, Colleen, is associated with more than one output. I hope you can catch on to that and see the difference there. All right, some more definitions here. The set big X, in other words, all the inputs, is called the domain. And the big Y, meaning all of the outputs, the whole set of outputs, is called the range. All right. There's also a couple other words here. When a little x is corresponding to a little y, meaning one input is associated with one output, the output is also called the value of the function at that input. So if you had the output, if you had the ordered pair 3, 5, then you would say 5 is the value of the function at 3. 3 is the input, but the actual value of the function there is the output. It's 5. Okay, another way to say it is the image of x. So you could say 5 is the image of 3. That's another way to say that. All right. Let's look back at example 1 now and decide whether this is a function. The simple question you can ask yourself is it perfectly predictable according to input? Is there any debate if you set a particular input? Would there be any debate or question as to what the output would be? So if I said Alaska, Arizona, California, all the way down to North Dakota, if I asked you any of those, would you be able to clearly say without doubt what the output is? The answer is yes, it is a function, because each one of these inputs is associated with only one output, and therefore it's perfectly predictable according to input. It's a function. All right, notice this element here of the outputs, this 1 has more than one input associated with it, but that's okay. That doesn't have anything to do with a function. An output can have more than one input associated with it, but the inputs can only have one output associated with it. Example 2, is this mapping a function, or is it just a relation? It is a function because each one of these inputs is associated with only one output, so it's perfectly predictable according to according to input. All right, now look at figure 7 and figure 8 and decide if they are functions or not. Go ahead and pause it and try it yourself. All right, figure 7 is a function because each of these inputs has only one output. Figure 8 is not a function because 0.71 carats in this particular set can have more than one output. Because there are other factors going on. I don't know if any of you guys have ever, maybe one day you'll get the privilege of shopping for an engagement ring, as I have had the privilege of doing. And you will discover, if you haven't learned this already, I had to learn this, that I think there are 4 C's, the 4 C's of diamonds. I think I have that right. I may be wrong, but if I'm wrong, forgive me. But the C's, the 4 C's are carats, that's the size, color, so like, is it perfectly clear? You know, is it white, clear, blue? Does it have yellow in it? Pink, whatever. Clarity, so like, are there any imperfections in there? And the 4th one, what is that 4th C? Color, clarity, carats, and cut. Oh yeah, cut. So is it how well cut is the diamond? What kind of size? What kind of shape is the diamond cut? Anyway, so all those things have to do with this cost, not just the carats. That's why it's not a function. The price of a diamond is not just a function of carats, which is why these inputs can have different outputs, more than one output. All right. I hope that made some sense. Look at example 3 down here. Look at A, B, and C. It's 3 different sets of ordered pairs. You're going to decide for each one of these, does it represent a function? All right, for part A, it is a function because each one of these inputs, meaning the first number in the ordered pair, has only one output with it. So 1, 4, 2 is only with a 5, 3 is only 6. What about part B? It is also a function. Again, because each one of these first numbers is listed with only one output. All right, what about part C? Part C is not a function. Why? Because -3 is listed with 2 different outputs. -3 is listed with a 9, and it's also listed with an 8. So it's not perfectly predictable according to input. If I said, what's the output if the input is -3, there would be some doubt there, some question marks. All right, now, what if -3 was listed not with a 9 at the first one and also with a 9 again the second time? Then it would still be a function because it would still only be listed with one output. Can you determine just by looking at an equation whether that equation represents a function? Most of the time you can decide that. Yeah. The question is, if I put a number in for X, how many answers could I get for Y? All right, look at example 4 here. If I put a 0 in for X, how many answers am I going to get? I'm going to get -5, and that's just one answer. If I put a billion in for X, how many answers am I going to get? I'm just going to get one answer. What if I put in -1 billion? I'm still just going to get one answer. So no matter what you put in for X, you're always just going to get a single output, a single answer for Y. So it is a function. But look at example 5. Determine if this represents a function. All right. Well, it's harder to tell with this one, but what we need to do is we need to get Y by itself, and we'll be able to tell better whether or not this is a function. So to get Y by itself, we move the X squared over as they've done here, and then what do we do to get Y by itself from this step? We will take the square root of both sides, but when you take the square root of both sides, you have to put plus or minus in front of this side over here. Okay, now, if I put in a number for X, how many answers am I going to get for Y? In almost every case, I'm going to get 2 answers for Y, right? If I put in whatever I put in for X here, 1 minus that will be the thing under the root. Then I take the square root of it. I'm going to get usually some decimal, but it's going to be plus or minus. So I get positive that answer and negative that answer, which is 2 different outputs for that input. So that's not a function. All right. Functions are often denoted by letters such as little f, little g, big G, and others. If f is a function, Then for each number x in its domain, the corresponding image in the range is designated by the symbol f with the parentheses with the x in it. But you read that as f of x. So whenever you put an x in there, whenever you put a number in there, the output is designated as f of that thing. Like f of x, or f of 5, or f of 100. All right, or you could also say f at x. So the function value at that value of x, f at 100, f at 5. We refer to f of x as the value of f at the number x. So if I said f of 5 is 20, then 20 is the value of the function f at the number 5. All right, f of x is the number that results when x is given and the function f is applied. Notice this. Make sure you don't think that this f with a x in parentheses does not mean f times x. It does not mean f times x. It's just a different notation for expressing a function value. That this output it depends on x. It's going to take x into it. It's going to spit something out. So we use that function value to say that, the function notation, a lot of times instead of the y variable. All right, just a couple more definitions. The variable x can also be called the independent variable because it can be assigned to any of the permissible numbers from the domain. But the variable y is called the dependent variable because its value depends on what x is. All right, so you put whatever you want to in for x, it's independent. But then y is dependent because it's going to take its value from what you put in for x. Another vocabulary word, the x variable or the independent variable is also called the argument of the function. So we got lots of synonyms here. Let's see if I can tell you what these synonyms are. I've written down some synonyms here. For the x variable, we have all these words associated with it. Input, argument, independent variable, and all of those x's represent the domain of a function. For y, or f of x, or image, output, dependent variable, and the whole set of those y's is the range of the function. All right, example 6. All right, we have to do all of these letters for example 6 here. So it gives me f of x. It defines that function as 2x squared minus 3x. And then it tells me to evaluate all these different ways to put something into that function or manipulate that function in some way. So part A, f of 3. If you want to pause the video at any point to review or to try to work ahead of me, that's totally good. So f of 3 is equal to 2. This means I'm putting 3 into the function. I'm inputting 3 into that function. That's what's going into the machine. And so it's going in the place of x, and the machine's going to do various things to it. All right, according to how it's defined. So I'm going to follow the order of operations here. Please excuse my dear Aunt Sally. So I square the 3 first, and that makes 9. So 2 times 9. I shouldn't have written x there. I should have written 3. So that should have been a 3 going in for that x as well. Minus 3 times 3. Now I can do my multiplication. So I can go ahead and make that 18. I can go ahead and make that 9. Then I can subtract and get 9. So part A, the answer is 9. Part B is f of x minus f of 3. So f of x, what is f of x? Well, it's already given to me up here. It means I'm putting x into the function, into the machine, and I already know what that's going to give me. That's going to give me 2x squared minus 3x, because it's already defined up there according to x. Minus f of 3, well, what is f of 3? It's what I already got in part A. So minus 9. And that is the answer for part B. Part C, 3 times f of x. It means I'm multiplying now. So notice the 3 is on the outside of the function. So I'm multiplying the whole function by 3. So I'm doing 3 times this function 2x squared minus 3x. And so that gives me, I'm going to distribute the 3. It gives me 6x squared minus 9x. All right. Part D, I'm doing f of negative x. So I'm putting negative x into the function. So everywhere there's an x, it gets replaced with a negative x. And then I simplify. What is negative x squared? It's negative x times negative x. Well, that's positive x squared. So that times 2 would be 2x squared. And what's negative 3 times negative x? It's plus 3x. So that's part D. Part E, the negative is on the outside. I'm multiplying the whole f of x function by that negative. So it's negative, and then that's 2x squared minus 3x. So I'm multiplying all that by a negative. I'm distributing the negative. I'm getting negative 2x squared plus 3x. All right, so that is part E. Part F, this time I'm plugging in 3x to the machine. So everywhere there's an x gets replaced with a 3x. So 2 times 3x squared minus 3 times 3x. So that's going to be, I got to order of operations, I got to square the 3x first. So 3x times 3x, that's 9x squared. So 2 times 9x squared minus 3 times 3x. Now I can multiply. It's going to be 18x squared minus 9x. And that is the answer to part F. All right, part G, f of x plus 3. That means I'm putting x plus 3 into the machine. So everywhere there's an x, it gets replaced by an x plus 3. All right, so x plus 3 squared. I've got to do x plus 3 times x plus 3. That's the FOIL method or double distributive. I'm going to go ahead and write it because you already know how to do that. It's going to be x squared plus 6x plus 9 minus 3 times x plus 3. Now I can distribute my 2 here and my negative 3 there. That gives me 2x squared plus 12x plus 18 minus 3x minus 9. Combine like terms, 2x squared plus 9x plus 9. All right, part H. Part H is a calculus, kind of an introduction to a calculus topic, but that has to do with these functions. I would really love to tell you about it. In fact, I will. If you want to skip ahead, you can. This will probably take 5 minutes. So if you want to skip ahead of this problem, you can. But if you're interested in it, go ahead and watch this next 5 minutes. All right, when we find the slope, right, the rate of change of a line, we just do the slope formula, right? x1, y1, x2, y2, and the slope formula is y2 minus y1 over x2 minus x1. And that gives me the rate of change of y with respect to the rate of change of x. So it's the rate of change of y with respect to x. But what if it's not a line? What if it's a curve? All right, what if it's a curve? And I want to find the rate of change, like here. All right, I can't find the rate of change there by doing the slope formula because the rate of change is different all over this curve, whereas with a line, it's always the same. But see, the rate of change is slower, like it's slower here, like it would be a slower rate of change here than it would be like here where it's steeper. Like way up here where it's going up quickly, the rate of change is higher than it is right here. All right, so what I'm going to do though, is I'm going to make another point right here. All right, and I'm going to call this point is going to be called x f of x. Instead of xy, it's called f. It's called x f of x. And this point over here, I'm going to call it, or imagine, okay, here's my set of coordinate axes. Here's x, right? F of x. That's that ordered pair. But let me slide over how much? Let's call it h. Let's call it h, the amount that I slide over here. So that this is the value x plus h. So this is x plus h. And so this value, the y value here, is f of that. It's f of x plus h. f of x plus h. So this is my ordered pair for my second point. This is my ordered pair for my first point. Okay. Now, find the slope between those 2 points. It's still going to be y2, it's still going to be this, but the y2 is f of x plus h. F of x plus h minus the y1 is going to be f of x. Okay, that's y2 and that's y1. And the x2, this is x2 and this is x1. So down here on the bottom it's going to be x plus h minus x. All right. Now the bottom will simplify because x minus x is 0. So this becomes f of x plus h minus f of x over h. And what we do in calculus is we say to make this be the instantaneous rate of change at this point, not between these 2 points, but actually at this point, I'm going to slide this other point closer and closer and closer and closer until it becomes infinitely close to that point so that they become the same point. Then I'm finding the rate of change between 2 points that are actually the same point. So I say that's the limit. I'm going to take the limit as h approaches 0. So I'm making h become nothing so that this is getting closer and closer and closer and closer and closer. All right, I'm giving you a lot of calculus language in a little bit of time, so I apologize for that. But it's just interesting. Maybe you'll find it interesting. If you take calculus one day, you'll have a little bit of a head start on the concept. This is called the limit definition of a derivative. The derivative finds the rate of change of a function at any point, the instantaneous rate of change of the function at any point. So let's apply that to this thing that we had up here, which was 2x squared minus 3x, right? So f of x equals 2x squared minus 3x. So if I want to do f of x plus h, that's going to be 2 times x plus h squared minus 3 times x plus h. That's going to be 2 times x squared plus 2xh plus h squared minus 3 times. I'm hurrying through this, but I mean that's just foiling is all that is. Distribute now 2x squared plus 2xh plus 2h squared minus 3x minus 3h. So that's f of x plus h. Now let me apply that down here. So this is going to be 2x squared plus 2xh plus 2h squared minus 3x minus 3h minus, that's the whole f of x plus h, minus f of x, which was 2x squared minus 3x. 2x squared minus 3x all over h. Make sure I got it. Yep. Now distribute the negative and watch the magic happen, okay? 2x squared plus 2xh plus 2h squared minus 3x minus 3h minus 2x squared plus 3x all over h. What happens? The 2x squareds cancel. The negative 3x and positive 3x cancels. So now I've got 2xh plus 2h squared over h. All right, factor out an h on top. Gives me 2x plus 2h all over h. The h's now cancel. I've got 2x plus 2h. And remember, it's the limit as h approaches 0. So if the limit as h approaches 0 means this h right here goes to 0. So that this whole term becomes 0. So the final answer is just 2x. So if I want to find the instantaneous rate of change at any point on that function, all I have to do is plug x, the x value at that point, into this right here, and it will give me the rate of change, the instantaneous rate of change of that function at that value of x. And that is beautiful and magical, and I love it. And I know that a lot of people don't, but that's okay. And that is an introduction to calculus. All right, moving on to college algebra again. Back to our topics. Okay, the next example wants me to find the domain. How do I find the domain of a function when I'm looking at the equation of that function? All right, let's read the definition of domain. Okay, often the domain of a function f is not specified. Instead, only the equation defining the function is given. In such cases, we agree that the domain of f is the largest set of real numbers for which the value f of x is also a real number. So it's any number x that you can put into the function, and when you put it in, it results in a real number also for y. And all of those values that you can put in for x are in the domain. But if you can't, if you put a value in for x and it results in a value for y that's not real, in other words, imaginary or something that's not defined as a real number, it's not defined, then it is not in the domain. All right, so how do we find the domain on these four functions here? So part A, the question is, what real numbers can we put in for x that result in a real number? What if I put in 1 billion? I'm going to get a real number. What if I put in -1 billion? I'm going to get a real number. What if I put in 0? I'm still going to get a real number. No matter what I put in for x, I always get a real number. So that means x is any real number. Or you can say, a short way to say that is you could say the domain is all reals. A pretty cool way to write all reals is with this what's called a double bar R. This is the symbol for all real numbers, for real numbers. So another way you can see that written is x is from -infinity to infinity. X is any real number from -infinity to infinity. That's another way to say that. All right, part B, it gets a little more interesting. Okay, now we got g of x equals 3x over x squared minus 4. The question you ask yourself in a problem like this is, can a fraction ever become weird? Like, what can make a fraction go crazy? If you have 0 on the bottom. If you have 0 on the bottom, the fraction is undefined. So what we want to say is we want to say the domain is all x such that, all right, this long vertical bar here means such that. It's kind of a shorthand way to say this. This means all x such that what? Such that the bottom, such that x squared minus 4 does not equal 0. Okay, then you got to actually figure out what x is by doing the algebra to get x by itself in this non-equality. So you add 4, you get x squared does not equal 4. Then you square root both sides, and you get x does not equal plus or minus 2. So the domain is this. It's all x such that x does not equal plus or minus 2. You could also see that written as an interval. If x doesn't equal plus or minus 2, it can equal any other number besides those. So you can say it's anything from -infinity to -2. And you put a parenthesis on the -2 to make sure you're saying I'm not including the -2 itself, but anything between -infinity and -2 is in there. Union -2 to 2. So anything between -2 and 2. Union 2 to infinity. So every number except these numbers where these parentheses are. So that's another way to write that answer. All right, part C. H of t equals the square root of 4 minus 3t. What can make a square root weird? What can make a square root be not real, not a real regular old real number? Well, a negative under the square root would do that, right? Because then you're going to get an imaginary number. So you say that the domain of this function is all t such that what? Such that 4 minus 3t, that's what's under this radical, such that that has to be what? It has to be greater than or equal to 0. Because if it's less than 0, it's going to give you an imaginary number because it's a negative under the radical. So we say that it has to be greater than or equal to 0. And then we solve for t. We subtract 4. We get negative 3t. It's greater than or equal to negative 4. We divide by 3. And t is greater than or equal to negative 4/3. So there's my domain. Or you might have to write it as an interval. You could say, how do you write this as an interval? That means that t can go from negative 4/3 to infinity. But I can put a bracket on the negative 4/3 because it can be negative 4/3. Negative 4/3 gives you 0 itself, and the square root of 0 is just 0, and that's fine. You just can't have a number less than 0. So negative 4/3 is okay, and I always put a parenthesis on the infinity. All right, part D. F of x equals the square root of 3x plus 12 over x minus 5. Okay, this time we have two possible weirdnesses, two possible weird things going on. I got a radical, so what's under that radical can't be less than 0. It's got to be greater than or equal to 0, and also have a fraction with where the denominator of that fraction can't be equal to 0. So I'm going to have to say both of those things. I'm going to say the domain is all x such that 3x plus 12 is greater than or equal to 0, and x minus 5 is not equal to 0. Solve both of these. 3x is greater than or equal to negative 12, divided by 3. X is greater than or equal to 4. Solve this one, plus 5 plus 5. X is not equal to 5. So we have two conditions. One, x must be greater than or equal to 4, but it can't be 5. So anything greater than or equal to 4 except 5. So these two expressions here represent my domain. And if I write that as an interval, I would say it's supposed to be a negative 4, right? Where's my negative sign? I thought I had a negative sign. Maybe it went away. All right, so anything greater than or equal to negative 4, but not 5. So I would say negative 4 to 5. I've got a bracket on the negative 4, a parentheses on the 5. It can be negative 4, but it can't be 5. Anything between negative 4 and 5 is good. Union 5 to infinity. And that's another way to express that domain. Look at example 9. It says finding the domain in an application. In other words, in some sort of a real life kind of thing. It says express the area of a circle as a function of its radius and find the domain. Well, the area of a circle as a function of the radius A of r, area as a function of radius, is equal to what when it comes to a circle? It's equal to pi r squared. So that is the area of a circle as a function of its radius. What about the domain? In other words, what are the possible values for the radius? What can the radius of a circle be? All right. It can't be negative. The radius of a circle can't be a negative value. It has to be positive. What about 0? Could it be 0? Could the radius of a circle be 0? It can't be that either, because if it was 0, it wouldn't be a circle, it would be a point. So we would say the domain is all r such that what? Such that r is greater than 0. Or you could say 0 to infinity. So sometimes the domain, like if it's just a math problem on paper, no application of the problem, you just do it mathematically like we did the last few examples. But if it applies to something like geometric, like the area of a circle, then it may be that the problem itself is what determines the domain. the application itself. Like if I was building a shed and I was trying to determine the height of the shed, you know, I know that the height of that shed is going to have to be taller than my lawnmower, but I know that it can't go above the height of my house if I'm building on the side of my house. So I would have a domain that would be limited by those conditions. Sometimes that's the case. Two more things to go over here. More definitions. In general, when a function f is defined by an equation in x and y, we say that the function f is given implicitly. If it is possible to solve the equation for y in terms of x, we write y equals f of x, and we say that the function is given explicitly. Here's an example. Here's the implicit form of a function. 3x plus y equals 5. The function y is a function of x, but it's not explicitly defined as a function of x here. It's implicitly defined because the 3x and the y are on the same side. But you could solve for it, move the 3x over, and you could get now y is equal to negative 3x plus 5. Now y is explicitly defined as a function of x. And so you could write it as y equals f of x. In other words, it's an explicit function of x, which is defined as negative 3x plus 5. All right, here the same way, move the x squared over, divide by the negative. This is given implicitly, but here is the explicit form of that same function. Here, divide both sides by x. This is the implicit form, but if you divide both sides by x, you get y equals 4 over x. That's the explicit form for y as a function of x, f of x. All right, last example for 3.1. We have two functions f and g. We can do things to combine these functions. We can add them, subtract them, multiply them, divide them. We can do other things, but those are the four things we're going to do in this example. So f plus g of x, part A, f plus g of x just means I'm going to add these two functions together. It's going to equal 1 over x plus 2 plus x over x minus 1. And I want to simplify that expression. And the way that I do that is by getting a common denominator. So the common denominator here, I'm going to have to multiply this by x plus 2 on bottom and top. And multiply this one over here by x minus 1 on bottom and top. That way my two denominators will be the same. That gives me x minus 1 on top of that. You don't have to distribute these on bottom. You can just leave these separate. If you want to distribute them, that's fine, but you don't have to. But I do have to distribute on top. That's going to give me x squared plus 2x. The reason I have to distribute on top and I don't have to on bottom is because I have to combine my like terms on top when I add the two fractions together, but the bottoms are just going to stay the same. So that's going to give me, when I combine the two tops together, it's going to be x squared, but then that x adds with that 2x to get plus 3x, and then minus 1 over x minus 1, x plus 2. So I have now found f plus g of x in its simplest form. Now it asks me to also find the domain. What is the domain? The domain will be all x such that x minus 1 times x plus 2 cannot equal what? Cannot equal 0. So then I say, well, that's not equal to 0 when this and this both does not equal 0. So I say x minus 1 doesn't equal 0, and I say x plus 2 doesn't equal 0. So I add 1, and I get x doesn't equal 1, and I subtract 2, and I get x doesn't equal negative 2. So I get the domain is x does not equal 1 or negative 2. Or if you wanted to write it as a interval, it would be negative infinity to negative 2, because negative 2 comes before 1, union negative 2 to 1, union 1 to infinity. That's another way to write the domain. All right, part B. Part B is very similar. I'm just subtracting them instead of adding them. So 1 over x plus 2 minus x over x minus 1. I've already gotten the common denominators in part A, so I'm just going to use the work that I've already done. So it's going to be x minus 1 over x minus 1, x plus 2, minus x squared plus 2x. I need those parentheses. Over x minus 1, x plus 2. Don't forget here that I need to distribute that negative into the top of this fraction. So I'm going to make that into a positive. And I'm going to change that to a negative x squared and that to a negative 2x before I combine my like terms. So now, combine the like terms, I get negative x squared, and the x and the negative 2x, x plus negative 2x makes minus x minus 1 over x minus 1, x plus 2. So there's my answer for that one. What's my domain? Since I have the same exact denominator as I had in the previous problem, the domain is the exact same domain that I got in the previous problem. Part C. It's 1 over x plus 2 times x over x minus 1. When you multiply fractions, you don't have to get a common denominator. You just multiply straight across. So the 1 times the x is x, and the x plus 2 times the x plus 1, I can just, again, I could distribute it, but I could also just leave it separate. And I'm going to leave it separate. So this is my answer. What's the domain? It's the exact same denominator as before, which that's the only thing that affects the domain. So again, same domain as the previous problem. And finally, part D. F over g of x. That means 1 over x plus 2. I'm dividing these things. 1 over x plus 2 over x minus 1. How do you divide fractions? Keep, change, flip. Case F. Keep the first fraction, 1 over x plus 2. Change the division to multiplication and flip the second fraction. So that's going to be x minus 1 over x. So that's going to be multiply straight across. I get x minus 1 over x times x plus 2. If you distribute the x, you get x squared plus 2x. That's fine, or you can leave it separate. But this is my answer for part D. But I do have to do some work here for the domain, because this denominator is not the same as the previous three. So I do have to do a little extra work here. Domain is all x such that x times x plus 2 does not equal 0. So that means that this can't equal 0 and this can't equal 0. So x does not equal 0 and x plus 2 does not equal 0. Subtract 2 here. X does not equal negative 2. So my domain is x does not equal 0 or negative 2. Or as an interval, you could write it as negative infinity to negative 2. I wrote the negative 2 before the 0 because negative 2 comes before 0 as I work my way from left to right, starting at negative infinity. Union, negative 2 to 0. Union, 0 to infinity. All right. That is all the examples for 3.1. You can read a summary, kind of a summary of what we just went over here. If you want to read this summary to kind of help you synthesize what we just learned, feel free to do that. Good luck on 3.1 assignment. I'll see you again in 3.2.